All right, we're going to talk a little more about growth and compounding, but no, we're going to do it in reverse, just to shake things up a little bit. Last time we calculated that 500 growing at 5% per year for 15 years is going to be worth 1039.46 by the end of the period. So if somebody asked you if 500 were invested at an interest rate of R for 15 years and that's worth 1039.46 at the end, what was the interest rate? You can figure that out. I mean, you just did it. The answer is obviously 5%. But if we hadn't just done the calculation, if we had some general problem, well, how would I do the answer? A little mathematics. Set an equation, 500 times 1 plus r to the 15th power equals 1039.46, and solve for r. How? Just remember a little algebra. I have some number x to the 15th power. How do I solve for x? I have to take the whole thing to the 1 over 15th power. You should remember doing that for lower powers. If you have x squared equals something, how do you solve? You take the square root. And remember the square root is to the 1/2 power. And you got to remember your algebra. I mean, ultimately, we can ask the question how to find z given that some amount z is invested at 5% for 15 years and it's worth 1039.46 at the end. That's a little easier algebra. Z equals 1039.46 divided by parenthesis 1 plus 0.05 all to the 15th power. Now, the reason we do this in reverse is because we often want to do discounting, which is discovering what is the value right now of some amount of money in the future. For now, we're going to ignore things like risk or inflation. We'll add those complications later. Start with a really simple case. How much money do I need today to invest at some interest rate to get some W dollars at some date in the future? Now, from basic micro, the value of something is the opportunity cost. What do I have to give up in order to get something? In a simple case, if I can put $100 in the bank today at 3% interest rate and get $103 in 1 year, then the value of $103 in 1 year is $100 today, because that's how much money I have to give up right now, today, in order to get $103 in the future. That's why we call it discounting, because the value goes down. $1 in the future is not worth $1 today. $1 in the future is worth less than $1 today, because opportunity cost, because interest rates. So to put that all into more mathy terms, after t years, z dollars initially becomes z times 1 plus r to the t power. How do I find the present value? W equals z times 1 plus r to the t power. Solve for z. Z is w divided by parenthesis 1 plus r to the t. Or rewrite that as w times 1 plus r to the minus t. Again, that's how negative exponents work. Review your algebra if you don't recall all that. That's the present value. It comes up again and again and again and again in finance applications, because a lot of what Wall Street is doing is just saying, okay, somebody can get money in the future. How much is that worth right now? That's just discounting. All right, you can pause the video and do these little problems. If R is 4%, what's the present value of $100 paid after 10 years? We know it would be less than 100, because $100 paid in 10 years ain't worth $100 now. I can put some money in the bank, get 4%, and let that compound for 10 years. I can start off with less than 100. So what is the present value of $100 paid at the end of 50 years at an interest rate of 4%? What's the present value of $100 paid at the end of 100 years at 4%? You should be able to calculate all those. You will note that the answer will get smaller and smaller because of compounding. Even a small amount of money in the bank today, compounded over 100 years, will be worth a lot by then. So pause and do the calculations. I'll be right here. Since the value is going down and down as the time to compound goes up and up, we might suspect that it will converge to some value as time goes to infinity. Yep, like the last video, we're going to do this an infinite number of times again. What's the value of W dollars paid next year, and the year after, and the year after, and the year after, on and on forever? We can use our math brain or algebraic brain to know the way the exponents work. If I take some number that's bigger than 1 and square it, it gets bigger. If I take some number bigger than 1 and take it to the 10th power, it gets a lot bigger. Take it to the 100th power, it gets a lot bigger, and so on. But if that's in the denominator, 1 divided by some gigantic number, that gets closer and closer to 0. The sequence terms, w over 1 plus r to the first, plus w over 1 plus r squared, plus w over 1 plus r cubed, plus w over 1 plus r, on and on to the t power. As t gets bigger and bigger and bigger, that term is going to get smaller and smaller. So it's reasonable to think that it might converge to something. Suppose it does converge, call it x, and then do a bit of algebra to solve for x. Find x equals 1 over r. So if r is 5%, then x is 1 divided by 0.05, 20. If r is 4%, then 1 over 0.04 is 25. As x gets bigger, as r gets bigger, x is smaller. Again, that's a common feature of discounting. Now, there's another way of thinking about that, perhaps a little more fun. Suppose I win the lottery. And let's say I get $10 million right in the bank. So I want to know, how much could I take out every year forever if I never touch the principal? Obviously, it depends on the interest rate. If the interest rate were 10%, and if I got 10 million in the bank, I can take out $1 million a year and never touch the principal. If the interest rate is 5%, then I can only take out $500,000 a year. If the interest rate is 3%, then I can take out $300,000 a year. So going back to the opportunity cost argument, what's the present value of $300,000 paid each and every year forever if the interest rate is 3%? That's 10 million. So see, these different viewpoints give us the same answer. So that's the good news. All right, a quick reminder on percentages. You should know this, but just a case. Percent is a convenient way of writing a decimal. You just move the decimal place. 15%, you move the decimal place 2 points, so it's 0.15. 99%, 0.99. 150% is 1.50. Just move the decimal point. 1% is 0.01. 0.3% is 0.003. It's very mechanical. We're just moving the decimal point. But later on, we'll talk things like U.S. inflation data, where it's commonly reported as, for example, 0.2%, which means 0.002. So we use percentages to compare two numbers as well. If A is half the size of B, then A is 50% of B. If A is a quarter size of B, then that's 25%. If something is increasing, there are a variety of ways of expressing that. If Z is 125% the size of Y, then that means Z is Y plus a 25% increase, or Z equals 1.25 multiplied times Y. Now, sometimes you got to look a little extra carefully to make sure you're not going too fast and getting sloppy. A lot of stores, when they're putting stuff on sale, they count on the fact that people are fast and kind of sloppy thinking. A store might advertise sale, 50% off, and then take an additional 25% off. Sounds good, right? But does that mean you get 75% off the regular price? Nope. That's a trick. It's right there in the words, but you got to read the words carefully to see the trick. Maybe it's easier to think about the extreme version. If they offered 50% off and then take another 50% off, would that mean they're giving away for free? No. That means it's a quarter of the price, right? They take half off and then another half of the remaining half, where half the half is a quarter. So if they say take 50% off and then take another 50% off, then that's a total of 75% off. Or going back to the original question, if the sale is take 50% off and then another 25% off, that means you take half off at the beginning and then a quarter of the remaining half, which is an eighth. So in decimals, you get it at 37.5% of the original price. Or what is 10% of 10%? You don't multiply 10 times 10 and get 100. Nah. You got to convert to decimals. So 0.1 times 0.1 equals 0.01, 1%. 10% of 10% is 1/10 of 1/10. That's 1/100th, or that's 1%. So you just got to be careful. Another thing to remember is exponents and logs. You've probably heard news items about some movie star, sports star getting paid, and you hear phrases like, they signed a 7-figure deal, which means that person got paid 7 digits worth of money, some amount between $1 million and $9,999,999. That's implicitly using a log scale. We could measure our own salaries in the same way, but you and me and most people we know are getting 2 digits per hour. That's just not as exciting way of putting it. But, somebody graduating might get paid an annual salary in the high 5 digits, and then after a few years of work, get to 6 digits. It's still pretty good. But all that's using a log scale implicitly. Log base 10. Now, if you remember your math courses, we often use log base E because reasons, a lot of reasons. The math works better, blah, 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 details. It's related to the fact that e to the r would have a constant percent growth rate. So on a log scale, that would just get us a line. So that's one of the reasons when we show graphs, we often show things on a log scale. So constant growth rates are going to be on a line. So see just these little bits of algebra that are worthwhile doing the mental archaeology, scraping off the layers of other things that accumulated on top of that, and remembering what's down there at the bottom.